In order to fully understand how de-icing chemicals do their work on roadways, let's review some basic physics and chemistry. If the H2O molecule, or as we know it, the water molecule, were visible, you'd see an oxygen atom with two hydrogen atoms attached. In this asymmetrical molecule, the two hydrogen atoms have a positive electrical charge, while the oxygen end of the molecule is negatively charged. In their gaseous state, water molecules move so fast they bounce off each other and never become attached. In their liquid state, water molecules are moving too fast to stay locked into crystals, but slowly enough to be attached to each other. In their frozen state, or as ice, water molecules are locked together in six-sided or hexagonal crystals. Individual molecules are vibrating, but they aren't going fast enough to break out of the crystal. The attraction of the positive hydrogen atoms of one molecule to the negative oxygen atom of another holds the crystal together. Now that we understand how water turns to ice, we can better understand how de-icing chemicals destroy ice crystals. This is what the salt or sodium chloride molecule looks like. It is made up of one positive charged sodium ion and one negative charged chloride ion. When salt is applied to the ice and there is moisture or water present, the sodium chloride molecule begins to break apart into positively charged sodium and negatively charged chloride ions. The negatively charged oxygen atoms of water are attracted to the positive sodium ions in the salt. The positively charged hydrogen atoms of water are attracted to the negative chloride ions in salt. Because water molecules are more strongly attracted to sodium and chloride than to each other, they unlock from their ice crystal formation even at temperatures below 32 degrees Fahrenheit, when in the presence of the sodium and chloride ions. This attraction destroys the structure of the ice crystal and dissolves the salt, resulting in a liquid salt and water solution, or brine. Therefore, de-icing and anti-icing chemicals like sodium chloride work by lowering the freezing point of water. The actual freeze point of a solution is governed by the concentration of salt in that solution. This is illustrated by this phase diagram, which has temperature on the vertical axis at the left and the solution concentration percentage for sodium chloride along the horizontal axis at the bottom. The diagram shows the temperature at which various concentrations of brine change phase, from liquid to solid or freeze. For example, at 20 degrees, a 10% solution of sodium chloride could melt ice. The freezing point continues to decline down to a -6 degrees when the concentration reaches 23.3%. This is what's called the eutectic temperature of sodium chloride. -6 degrees is its maximum freezing point depression. Note that as the concentration increases beyond 23.3%, the freezing point of the liquid chemical rapidly increases. This ability to lower the freezing point of water is a unique feature of de-icing chemicals, and each de-icing chemical has its own special characteristics. The eutectic temperature of calcium chloride, on the other hand, is -60 degrees. A 29.8% solution of calcium chloride doesn't freeze until it reaches a -60 degrees. It is this freezing point depression characteristic that makes de-icing chemicals so useful, and why sodium chloride and calcium chloride are called freeze point depressants, because they depress the freezing point temperature of water. Antifreeze in your vehicle is also a freeze point depressant. As we all know, water freezes at 32 degrees Fahrenheit. Straight antifreeze freezes at 2 degrees. However, when you mix 50% antifreeze with 50% water, the freeze point temperature of the mixture is lowered to -35 degrees. Like antifreeze, de-icers are less effective when too little or too much is used. The phase diagram best illustrates this and provides important principles that come into play every time you are out on the highway applying rock salt or brine. Anytime you apply salt, and the combination of solution concentration on the roadway and road temperatures fall into this green area, you have applied the right amount of chemical and the melting of ice will take place. If the combination of solution concentration and temperature are in the red area, ice is going to form because the solution concentration is not high enough to melt all of the ice. If the combination of temperature and solution concentration falls into the blue area, the material you apply will have no effect until more moisture is present to dilute the concentration. In the yellow area, below -6 degrees, melting will not take place at all. The salt will sit on top of the ice, no matter how much salt you apply, until the pavement temperature warms. The phase diagram also provides an understanding of how de-icing and refreezing can occur on a pavement. Let's say you apply brine to an ice-covered pavement that is 20 degrees. As long as the temperature remains at 20 degrees and the brine concentration is 23.3%, you are in the green area, and melting is going to occur. However, as the ice melts, the brine is diluted, and as soon as the concentration percentage drops below 10%, you begin moving into the red area, and the melted ice will begin to refreeze. Even if brine concentration remains high, let's say 20%, but the temperature begins to rapidly drop, you can see that refreezing will occur as soon as the pavement temperature hits 3 degrees. Take time to fully understand the phase diagram, because the principles it illustrates will come into play every time you are out on the highway applying de-icing chemicals. When a solid de-icer like salt is applied to an ice-covered pavement, it must first dissolve and become a solution before melting can occur. The moisture can come from pre-wetting the salt or from moisture on the highway. Calcium chloride, as we have learned, can draw moisture from the air to begin the melting process. However, too much moisture can rapidly slow or halt the melting process. Dilution of the solution quickly reduces melting power. Let's say you have just laid down 300 pounds of straight salt per lane mile, and there is a mere 0.02 of an inch of moisture on the roadway surface. The concentration of the salt solution present on the roadway will be 16.8%, and the freeze point will be 12.5 degrees. If just 0.03 of an inch of additional precipitation falls, bringing the total to 0.05 of an inch of moisture, the concentration drops nearly 10 percentage points to 7.17%, and the freeze point rises 12 degrees to just under 24 degrees. If you remember that salt brine at its most powerful concentration is a 23.3% solution by weight, you can see that dilution of de-icing chemicals can have a serious impact on their ability to melt ice. Dilution of solution always takes place as melting occurs or additional precipitation falls, whether it be in the form of rain or snow. Dilution of solution must always be considered when applying dry and liquid de-icing chemicals. In theory, you could calculate the exact amount of de-icing chemicals to apply if you knew the pavement temperature, the amount of ice the chemical must melt, and the amount of chemical that would stay on the roadway. However, changes in weather or traffic often alter those calculations considerably.